Welcome to the session on cloud computing and its application. In this session, we'll be talking about Module 5, Chapter number 10. Name of the chapter is Cloud Applications. In cloud application, we'll be talking about different types of cloud applications, as you can see in the slide. Cloud computing has gained huge popularity in industry due to its ability to host applications whose services can be delivered to customers rapidly at minimal cost. This chapter discusses various application case studies dealing their architecture and how they leverage various cloud technologies, applications ranging from scientific to engineering domain, gaming to social networking, and so on. So now we will talk about scientific applications. Scientific applications are a sector that is increasingly using cloud computing systems and technologies. The immediate benefit seen by the researchers and academics is the potentially infinite ability of computing resources and storage at sustainable price if compared to a completely in-house deployment. In scientific applications, talk about healthcare, that is ECG analysis in the cloud. Healthcare is a domain where computer technology has found several and diverse applications, from supporting the business functions to assisting scientists in developing solutions to cure diseases. Here, in particular, we'll discuss ECG, stands for electrocardiogram data analysis on the cloud. ECG activity produces a specific waveform that is repeated over time, and that represents the heartbeat. The analysis of the shape of the waveform is used to identify a condition in which heartbeat within an whether it is irregular or abnormal rhythm, and it is mostly common way for detecting the heart disease. Cloud computing technologies allow the remote monitoring of the patient's heartbeat. Its analysis takes a minimum time and notify the person as well as the doctor for the first aid. This way, a patient at risk can be continuously monitored without going to the hospital for ECG analysis. At the same time, doctors and first aid persons can instantly be notified with cases that requires their attention. The diagram shown in the slide has a variable computing devices equipped with ECG sensors constantly monitor the patient's heartbeat. Such information is transmitted to the patient's mobile devices that will eventually forward it to the cloud-hosted web service for analysis. The web service forms the front end of the platform that is entirely hosted in the cloud. and that leverages the three layer of the cloud computing stack: SaaS, PaaS, and IaaS. The web services constitutes the SaaS application that will store ECG data into the Amazon S3 services and issues a processing request to the scalable cloud platform. The runtime platform is composed of dynamically scalable number of instances running the workflow engine and Anik. The number of workflow engine instances is controlled according to the number of requests in the queue of each instances, while Aneka controls the number of EC2 instances used to execute the single task defined by the workflow engine for a single ECG processing job. Each of these jobs constitutes of a set of operations involving the extraction of waveforms from the heartbeat data and comparison of waveform with the reference waveform is done to detect the anomalies. In case of anomalies, doctor and the persons can be notified to act on a specific patient. Now, what are the advantages of this? First advantage is the elasticity of cloud infrastructure that can grow and shrink according to the request served, so that as a result the doctors and the hospital do not have to invest in large computing infrastructure uh, designed after capacity planning, thus making more effective use of the budgets. The second advantage is ubiquity. Cloud computing technology have now become easy accessible and promises to deliver system with the minimum or no downtime. Cloud services are priced on pay-per-use basis with volume prices in case of large number of service requests. Next case study we will study is protein structure prediction. Application in biology often requires high computing capacity and often operates on large data set that can cause extensive input-output operations. Because of these requirements, they have often made extensive use of supercomputers and cluster computing infrastructures. Similar capabilities can be leveraged on demand by using cloud computing technology in a more dynamic fashion, thus opening new opportunities for bioinformatic applications. Protein structure prediction is a computationally intensive task fundamental for different types of research in the life science. Among these is the design of new drug for the treatment of diseases. The geometrical structure of protein cannot be directly inferred from the sequence of genes that composes its structure, but it is the result of complex computations aimed at identifying the structure that minimizes the required energy. This task requires intensive of space with a massive number of states and consequently creating a large number of computations for each of these states. The computational power required for a protein structure prediction can now be acquired on demand. A project that investigates the use of cloud technologies for protein structure prediction is JIVA, as shown in the figure. The prediction task uses machine learning techniques for determining the secondary structure of the proteins. These techniques translates the problem into pattern recognition problem where a sequence has to be classified into three possible classes, that is E, H and C. A popular implementation based on support vector machine divides the pattern recognition problem into three phases: initialization, classification and final phases. Even though these three phases have to be executed in sequence, it is possible to take advantage of parallel execution in the classification phase where multiple classifiers are executed concurrently. This creates the opportunity of sensibly reducing the computation time of the prediction. The prediction algorithm is then translated into the task graph that is submitted to the Aneka. Once completed, the middleware makes the results available for visualization through the portal. The advantage of using cloud technology versus conventional grid infrastructure is the capability of leveraging the scalable computing infrastructure that can grow and shrink on demand. Next case study we will be seeing is gene expression data analysis for cancer diagnosis. Gene expression profiling is the measurement of the expression levels of thousands of genes at once. It is used to understand the biological process that are triggered by the treatment at a cellular level. Together with the protein structure prediction, this activity is a fundamental component of drug design since it allows scientists to identify the effects of specific treatment. Another important application of gene expression profiling is cancer diagnosis and treatment. Cancer is a disease characterized by uncontrolled cell growth and pro, pro-life refresh cell growth. This behavior occurs because of mutation of the genes that regulates the cell growth. This means that all the cancer cells contains mutated genes. In this context, gene expression profiling is utilized to provide a more accurate classification of tumors. This problem is often approached with learning classifiers. This problem is often approached with learning classifiers as shown in the figure, which generates a population of condition action rule that guides the classification process. Among these, the extended classifier system XCS has been successfully utilized for classifying large data sets in the bioinformatic and computer science domain. However, the effectiveness of XCS when comforted with high dimensional data set has not given a much great results. So a variation of such algorithm CoXCS has been proved to be effective in these conditions. CoXCS divides the entire search space into subdomains and employs the standard XCS algorithm in each of these subdomains. Such a process is computationally intensive but can be easily parallelized as the classification problems on the subdomain can be solved concurrently. Cloud-CoXCS is a cloud-based implementation of CoXCS that leverages Aneka to solve classification problems in parallel and compose their outcomes. The algorithm is controlled by strategizing, which defines the way in which the outcomes are composed together and whether the process need to be iterated. Because of the dynamic nature of XCS, the number of required compute resources to execute can vary over time. Therefore, the use of scalable middleware such as Aneka offers a distinctive advantage. Next case study, we will talk about satellite image processing. GeoScience application collects, produce and analyze massive amount of geosparticle and non-sparticle data. As the technology progresses and our planet becomes more instrumented, the volume of data that need to be processed increases significantly. In particular, the Geo Information System (GIS) is a major element of geoscience application. GIS application capture, store, manipulate, analyze, manage and present all the type of geographical referenced data. This type of information is now becoming increasingly relevant to wide variety of applications from advanced farming to civil security and natural resource management. As a result, a considerable amount of geo-referenced data is ingested into the computer system for further processing and analysis. Cloud computing is an attractive option for executing these demanding tasks and extracting meaningful information for supporting decision makers. Satellite remote sensing generates hundreds of gigabytes of raw images that need to be further processed to become the basis of several different GIS products. This process requires both input-output and compute-intensive tasks. Large size images needs to be moved from the ground station local storage to compute facilities where several transformations and corrections are applied. Cloud computing provides the appropriate infrastructure to support such application scenario. Figure shown in the slide integrates several technologies across the entire computing stack. A SaaS application provides a collection of services for such as geocode generation and data visualization. At the PaaS level, Aneka controls the import of data into visualized infrastructure and execution of image processing tasks that produces the desired outcome from the raw satellite images. The platform leverages a XZen private cloud and the Aneka technology to dynamically provision the required resources to grow and shrink on demand. The project demonstrates how the cloud computing technology can be effectively employed to offload local computing facility from an extensive workloads and leverage more elastic computing infrastructure. So overall, in this session, we have seen the four different types of scientific applications starting from ECG. Then we have seen protein structure prediction, in a gene expression data analysis for cancer diagnosis, and last one is satellite image processing. In the next session, we will be talking about business and consumer application. Thank you.